All right. So let me introduce you first to what we call a Lewis acid, right? Because there's different excuse me types of acids and bases. So the first thing I want to introduce you to is what we call a Lewis acid. All right. Now Lewis acid is not a typical acid. It's different in the sense of it is an electron pair acceptor. Right. So an electron pair acceptor. So it's an atom or an ion that can accept a pair of electrons. Most of the times when we think about Lewis acids, we think about metals, but you got other types of Lewis acids as well. Excuse me. Metalloids can also function as Lewis acids. Something like silicon is a great example of a Lewis acid. Boron is an example of a Lewis acid. We think about metals, we could think about something like, let's say magnesium 2+, the ion. So anytime you have an ion like this, like magnesium 2+, that means if it has a +2 charge, that means it has lost some electrons. So it's capable of accepting a pair of electrons. And then metalloids like silicon and boron, they accept electrons in empty orbitals. We're going to talk about orbitals in more depth, I think in the next chapter. So don't sweat that part about not really knowing what an orbital is. We'll talk about it. But it's basically, when we think about the shells that electrons reside in, so the orbitals are in those shells. All right, so Lewis acids, the way that they function, let's say you have something like this. So let's say acetone, and you have a metal, let's say, let's just use magnesium. Right, so this pair of electrons here can actually donate to that metal. So this is my Lewis acid. All right, and then excuse me, by the same token, you have Lewis bases, right? And a Lewis base is the opposite of a Lewis acid. Instead of being an electron pair acceptor, the Lewis base is the opposite. It's an electron pair donor. Sorry about that. My daughter's on spring break and she just got attacked by a wasp on the back porch. All right, so I'm leaving that on my YouTube when I upload it too. I'm not gonna cut it out. So a Lewis base is an electron pair donor, right? Or an electron donor. When you think about so basically any element or ion with a lone pair of electrons can be a Lewis base. Right? Any element or ion that has a lone pair. So you think about even the the acetone here, it has those pairs of electrons that can be donated. So that can even be considered a Lewis base. Right, and then of course you have, let's say you have a carbon with a negative charge. That's a Lewis base. If you have ammonia, nitrogen has a lone pair, so that can be considered a Lewis base. So basically anything that can donate electrons, we consider it a Lewis base. And so Lewis bases and Lewis acids kind of work in conjunction with one another, right? A lot of reactions that are done with the understanding that if I have a Lewis acid or a Lewis base together, then they're going to associate with one another. But it's not necessarily an ionic association, because sometimes, again, your Lewis acid might be neutral, like silicon, or it might be an ion. All right, by the same token, your Lewis base can be neutral or it can be ionic. But the point is that one accepts electrons and then one donates electrons. That's the main point I want you to take from this. All right, so then with what we're going to talk about for now and what we're adding to what we already know, and we're going to talk about Bronsted acids and bases. Right, and this is probably the more traditional definition or traditional description of an acid that you've heard before. Right, so Bronsted acids, these are what we call a proton donor. So you have a hydrogen with no electrons, we call that a proton. Just because that's the only thing that's left. If it doesn't have an electron, it has one proton in the nucleus, right? So a hydrogen ion is what we call a proton. And so Bronsted acids are proton donors. They give away H+. And a Bronsted base is an H+ acceptor. Right, so it's a proton acceptor. These two go hand in hand. If you have a proton, if you're doing an acid-base reaction, one of your reactants has to be the acid and one has to be the base. So that there's a way to tell those apart. And we're going to talk about that shortly, right? So in any acid-base reaction between a Bronsted acid and a Bronsted base, there's a proton transferred from the acid to the base. All right, so when you transfer a proton from the acid to base, that's what happens in an acid-base reaction. And I'm gonna show you an example in a second. But one other thing that we need to understand about acids and bases is this. If it's a strong acid, it's gonna completely dissociate. right? So if you take that acid and you dilute it up with water, it's going to dissociate completely, right? What that means is that we talked about this when we were doing those ionic equations, is the constituents that make up the acid will be torn apart, basically. So the waters will get in between the proton and its conjugate base. So let me show you that. And the same thing when we talk about Bronsted bases, it's going to be the same thing with that. Those bases also dissociate. If it's a strong base, it's going to dissociate completely. All right, so here's an example of a strong acid like HCl, right? And if I take that and dilute it up, so I'm going to add water to it, right? What happens is the right, the acid actually dissociates, right? But in this case, water is what we call amphiprotic. So it can be an acid or a base. So water can be an acid or a base. In this case, it's acting as the base. So when this acid dissociates, what you end up with is this. And I'm gonna write this out instead of just writing H2O, because I want you to see what happens. So this is the structure for water. Got 2 lone pairs on oxygen. We'll get into Lewis structures, I think, in the next chapter as well. Just so I think the next time I teach this, I'm going to move that up, because I think that's a really important skill set to have when we're looking at stuff like this. But it's okay. So this is water. So when water reacts with this acid, you end up with, and let me change this too. You end up with this as your oxygen is positive plus Cl minus. Right, so chlorine has 3 lone pairs here. Let me show you that too. Over here is going to have 4 lone pairs. I might as well show you how this works as well. So when you're doing acid-base chemistry like this, where your base is not necessarily a salt, like a hydroxide salt or some other type of salt, this is what happens. And this is the organic professor in me coming out. So don't panic about this, but I'll show you how it happens. So the water is going to use this pair of electrons here. To grab that hydrogen. It's going to attack it. And then the pair of electrons in the bond between hydrogen and chlorine, because every bond is made up of 2 electrons, those go back to the chlorine. That's how we end up over here with H3O plus and then Cl minus, right? So Cl picked up a pair of electrons from that bond. And most of your acid-base reactions are going to happen like this, where your base is going to use a pair of electrons to pull off that proton, right? So the H plus is going to leave with the base. So on the other side of the reaction, you have this, which we call the conjugate base. And then the hydronium, which is right here, which we call the conjugate acid. right? So this is my acid. This is my base. On the other side of the arrow, I have my conjugate acid and my conjugate base, right? Always, anytime you have an acid-base reaction, that's the result. The acid plus the base is going to yield a conjugate acid and a conjugate base, all right? So the conjugate acid is basically the base after it has pulled off H plus. So after it has accepted H plus, it becomes the conjugate acid. The acid, after it donates H plus, becomes the conjugate base. All right. How many can somebody tell me for lunch? Let me see where y'all are. The three of us who are here, but we got more people now. How do I know what the charge is on chlorine? And on the product side, how do I know that charge is -1?
Is it because there's no number in front of the charge?
Mm-hmm. That's true. But how do I calculate it? Let me say that. How do I calculate it? We talked about this. It was a long time ago.
By the valence electron.
Who was that?
Alexis.
Valence. So how do we use the valence electrons to calculate that charge? You're right. You're in the ballpark.
Oh Lord. It's by the is it atomic?
I get. Remember we had this little formula, right? It was valence minus what?
Atomic
Actually, yeah, atomic number.
Okay.
So the atomic number is going to tell me how many electrons are present, right?
Yeah.
So that's going to be the valence part. The actual is what's actually around the atom. So what's the valence for chlorine? What's the atomic number? What group is it in?
Oh my gosh. Is it I don't want to guess. I want to say 8.
No, 8 is noble gases. The halogens, which chlorine is a part of, is right next to a 7. So the
7.
So this is going to be the way we calculate this charge is to take that number 7 and subtract from it the actual number of electrons that are around chlorine. All right, so that's 7 minus, sorry about that, 8. So that's how I get that charge of -1. This is, if you remember, I know it was a while back, but this is an indispensable skill for this class and any other chemistry class where you're dealing with ions and elements. This is the form, what we call a formal charge. It'll make more sense when we start doing Lewis structures and building them from the elements and using the atomic numbers to determine how many electrons are present and stuff like that. But I'm still going, you can put your Cash App in the chat because you came as close as you could without actually getting it. So I'm still going to honor my word. All right, so that's a basic acid-base reaction where you have an acid and a base. In this case, it's water acting as a base, and that's going to give you a conjugate acid, which is the hydronium ion that I have shown, the H3O, and the conjugate base, which is Cl minus, right? So when you have a strong acid, again, that's going to dissociate in water completely. When you have a weak acid, it only dissociates partially. So let me put that up here. Right? So when we think about, let's do another example. When we think about acids and bases, let's do another example. So this is an example of a strong acid. When you, again, dilute it up with water, it is going to completely dissociate. So you'll have the ions in solution, right? But if you have a weak acid like acetic acid, which I'll show you we've seen this already where we have this, right? Which can also, might as well give you this free game so you can use it when you take organic. It also looks like this. So this is acetic acid. This is a very weak acid. This is basically what vinegar is. It's dilute, very dilute acetic acid. So if you take acetic acid and do the same thing, dilute it up, right? What you're going to get out is this, which is what do we call that? And we've seen this a bunch of times already. Sometimes, again, you'll see it written like this. Just saw this yesterday, as a matter of fact. So this is acetic acid. This is what we call the acetate ion, which is that on the other side of the arrow, is that the conjugate acid or the conjugate base? If this is my acid and water is my base, what is the acetate ion in this reaction? Is it the conjugate acid? Okay, let's think about that. So the conjugate acid, let's go back up here. If this was the conjugate acid, notice what happened. It started out as water. It picked up H plus from HCl, and now on this side, it has an extra proton, right? So the base is going to start out as the base and going to end up as the conjugate acid. That's how acid-base reactions work. When the base accepts a proton from the acid, it becomes the conjugate acid. When the acid gives up its proton, what's left over from that acid becomes the conjugate base. So if we go down here, we can see, and let me write this out again. Right, and so this is the proton is going to get given away by the Bronsted acid, right? So on this side, when I lose that proton, let me just show you how this happens. Right, so there's going to be this pair of electrons is going to come here and steal off that proton, and then this bond is going to break, and those electrons are going back to oxygen. And I'll explain all that when we get to organic, but for now, let's just think about it this way. All right. So this is how we show what you call a mechanism, where you show the arrows moving between atoms and the electrons being exchanged and all that. But I don't want to get too deep in the weeds with that. All right. So now once my acid gives up its proton, I'm left with this, which is the conjugate base. So the acid always becomes the conjugate base, and then the base is going to become the conjugate acid. And this oxygen is now positive, and now this is the conjugate acid. Period. All right, so that's the reaction right there. But this is actually, acetic acid is very weak. Right, only when you dilute this up with water, only about 1% dissociates. Only about 1%. All right, so one other thing I want to point out is here. When you do acid-base reactions, you always show them as an equilibrium. You're going to talk more about that in part 2 when you start dealing more in depth with acids and bases and rate laws and equilibrium constants and all that. But you always, an acid-base reaction is always in equilibrium. And this particular reaction, equilibrium is actually going to favor, and you can show this way, equilibrium is going to favor this side. So you can write that. Right, you can write it to show which side the equilibrium is. Kind of like thinking about this being on a seesaw. So if both sides were on a seesaw, the side to the reactant side with the acetic acid and the water, it's going to be like tilted this way. So we think about this in terms of reactants, and fix that. Products, right? This particular equilibrium is going to favor the reactants, right? So that's why the arrow going backwards is longer than the arrow going forward. It's really only about 1% of this is actually going to dissociate. All right, one other little piece of information about acetic acid, since they gave it to us, but they didn't explain it, is this, that is what we call an organic acid. What that means is that it's carbon-based, right? So the structure includes carbon. That's all that means. It's not organic in the sense of like what we think about organic when it comes to food with no fertilizer and no pesticides, no whatever. It's just that it contains carbon. So any molecule that's carbon containing, we consider it an organic molecule. All right. So some of your typical acids, really typical strong acids, HCl, obviously. Your halogen acids are all very, very, very strong acids. HCl, HBr, HI, really, really strong acids. So this is hydrochloric acid. This will be hydrobromic acid. Sorry about that. And this is hydroiodic acid. Right. And then you have other strong acids like nitric acid, super, super, super strong acid. Sulfuric acid, which we'll see a lot. And then phosphoric acid, which is also pretty strong. Right. So these are examples of strong acids. So anytime you dilute these up, they're going to ionize into the proton, which is H plus, and then whatever that counter ion is. Right. Because every one of these acids is basically, if I were to write this in ionic form, it will be H plus Cl minus. Right. Same thing here for phosphoric acid, it will be 3H plus PO4 minus 3. Sulfuric acid would be 2H plus SO4 minus 2. So when any of these acids ionize, this is, you'll get the, if you dilute them up in water, you're going to get the ions that are associated with them. All right. So now let's talk about, for a quick second, about bases. If you have a Bronsted base, that's a strong base. When you take a base and you dissolve it in water or you dilute it, right? Typically your base is going to yield a hydroxide ion. That's the most basic definition of a base. So a typical base will give a hydroxide ion on in the product once it's ionized. Right. So if you have let's say for instance, sodium hydroxide, and you dissolve that in water, right? It's going to ionize to Na plus OH minus. All right. And then by the same token, if this is a base, right? If this is my base, and then water in this case is acting as the acid, when it ionizes, right, the OH part of the base here is going to steal one of the protons from water. So that's where the other water comes from. And then that's why you also have a hydroxide ion on that side as well. All right. So most of the time, if you have a base, it's going to give an OH as one of the byproducts. So this is hydroxide. So the hydroxide anion is kind of proof that a base is present. Right? So any hydroxide salt is going to be considered a strong base. All right, here's a good question based on what we talked about with yesterday with the solubility. Which hydroxide bases are going to be soluble in water? Based on what we talked about yesterday. There's only two cases where the hydroxide ion doesn't form a precipitate.
Is it with the sodium?
Okay, sodium. So sodium is located where on the periodic table? What group? You're right. You're 100% correct.
Pull up my thing. I have left it.
It's the furthest group to the left.
Oh, so it's group 1.
Group 1. Hydroxyl is only soluble with group 1 elements and barium. That's it. Any other metal that it makes a salt with, or any other metal that it makes a salt with is going to be insoluble. So only group 1 and barium. All right, if you go back and watch that little solubility video, it was the very last part of that. All right, so when we say all OH salts are strong bases, they're not all soluble. So really what we're talking about is like KOH, sodium hydroxide, barium hydroxide. So salts that are actually soluble, because if you can't get it to dissolve and ionize, then it's not going to react with the acid. Right? So typical bases are going to give OH. They're going to ionize fully when dissolved in water. And weak bases are the opposite. Right? And this is weak in relative terms, because when I think about ammonia or other nitrogen-based bases, then I think of those as inorganic. Those are actually considered pretty strong bases. But in relative terms, like something like an ammonia, this will not fully ionize. So the equilibrium is going to lie to the reactant side. So this will be NH. NH4 plus OH minus. So let me kind of illustrate that. Come on, Russell. Right, so you can see here, this is water. In this case is going to be my acid. And then the ammonia is going to be my base. So over here, NH4 plus, the ammonium ion is the conjugate acid. And then the hydroxide conjugate base. Right? And the way this works is the same, all acid-base reactions, especially between weak bases like this, they all act the same way. They all just exchange a pair of electrons between the base and the acid. And there's a pair of electrons that's going to go back here. All right. So then we end up with ammonium and hydroxide. But again, this is not going to fully dissociate. So this is only partial dissociation. And that leads to some other stuff that's beyond the scope of the class, but we'll talk about that another time. All right, so we're gonna stop here. And then on Friday, we're gonna pick up with, show you a couple of examples of acid-base reactions, neutralization reactions, and then we're gonna pick up and start talking about redox reactions. All right, any questions about anything we talked about today? All right, if not, I'll see you all on Friday, God willing, and have a good rest of your afternoon, rest of your day. Do well in your classes, keep working hard. We got a few more weeks left, and then you'll be home free for the summer. So don't get tired, keep grinding. All right.
Professor, did you get my message in the chat?
Is this Alexis?
Yes.
Yes.
Okay.
I see it. I'm gonna keep my word. Don't worry.
Okay. No, because I know sometimes
run my coins. I got you.
Sometimes my Zoom messes up. So okay.
No, I got you. I'm looking right at it. I'm about to do it right now.
Okay. Have a good day.
All right. Take care. Y'all have a good one.
You too.
All right.